All right, we have some basic questions about sound. One of our first questions is, well, what can humans hear? Well, when I'm thinking about that, there's really two things I need to worry about. I need to worry about the frequency of the sounds, the pitch of what I can actually hear. Now, as a human being, human beings, we've talked about this previous to this, can hear about 20 hertz to around 20,000 hertz. So I have some tuning forks right here. So let me just bring them up to you here. Now, this particular tuning fork this is a note C. Now remember, there's different, there's a low C, middle C, high C, there's a lot of different ones. So this is 128 hertz, which means that there's 128 humpy things, you know, the peaks per second that go into your ear. So let's listen to this one. So it's really that humming sound that you're hearing, and you can actually see the tuning fork vibrate back and forth at 128 hertz. This is a relatively low sounding kind of pitch to it. All right, now let's try the middle one. All right, notice that this tuning fork is somewhat shorter than the other one. This is a 523, also a C. And if you listen to that, we've got ourselves a nice little...
Can I have your attention, please? Ms. King, please dial 0. Ms. Beth King, please dial 0.
higher pitch to it at 523. And finally, I have 1024, and this is an even higher pitch. And you can hear it's like more of a high whistling sound. Now, this is 1,000 hertz. We can hear up to around 20,000 hertz. So good luck with that. All right. So that's the frequency of the sound. Now that leads us to our next question. Well, we can hear certain frequencies, but what about how loud things are? So let's think about that. So as I'm speaking here, I'm going to lower my voice to a point for a loudness, and then let me see if you can actually hear what I'm actually trying to say here. So as I lower my voice, the loudness of the voice starts to get greater. So the question is, how loud can we actually hear? Now, I was thinking about this the other day. Originally, I thought my dog had ESP, where our minds were connected. So because I drove home, and then the dog would start to bark, actually. Let's say in the case of Mrs. Hessler arriving back at the house, the dog would actually know that Mrs. Hessler was going.
Clyde, please dial 0. Miss Clyde, dial 0.
Mrs. Hessler would be driving home. The dog would actually know before she arrives that she was coming up the driveway. And I'm looking around. How did the dog know that? It must be an ESP connection between the mind of Mrs. Hessler and the mind of the dog. And then I realized dogs can actually hear things that humans cannot. Dogs' ears are more sensitive than humans, so the dog actually could hear the car coming before I could. So the idea of this ESP type brain meld between Mrs. Hessler and the dog was actually false. All right. So the question is, how loud can I actually hear? So there's a thought here. If I were to take and make a sound of sorts, so let's say, you know, coming out of this your mouth, or you go, hey. So from that, we know that there's a compressional wave, a longitudinal wave that comes out like a slinky out in all these different directions. So if I think about the propagation of that particular sound, all of these slinkies start popping out and going in a variety of directions. So depending upon where you're standing in the room, it just depends on what slinky is actually going to run into your ear. So as the sound comes out of your mouth, it goes out in all these different directions, like so. Now, if I thought about it, instead of thinking it in terms of a slinky, if I had an infinite number of them, what I'm actually doing is forming a sphere. So when I say, hey, it's almost like a bubble came out of my mouth, all these slinkies going around in different directions. And as time goes on, doesn't the bubble keep getting bigger and bigger? And then eventually it hits your ear, and you go, oh, I heard what you said, Mr. Hessler. Great, great idea. So, well, if we think about the sound as it propagates, it kind of like forms this surface as it propagates out into the room in all different directions. So now I'm going to draw a sphere around this bubble like so. And we know that the sound goes out in many directions. So I'm drawing a flat view of it, but think of it though more as spikes coming out in all different directions surrounded by a sphere. All right, now the question is, well, how loud does it sound? Well, everyone knows as you go farther away, doesn't the sphere, the distance that you're traveling, doesn't it start to like get a little quieter, harder to hear? So if you could not hear me, you'd probably get a little closer and say, what did you say? You know, so as the distance increases, the sound gets quieter, so we know this. Well, the question is, why is that so? And the answer to that is, as we go through and look at various positions, let's take a look at, say, this position. If I was listening at this spot right in here, notice that two lines go through that particular area at any given time. Now, if I did, or went farther away like this, only one line would be going through that box at any given time. What does that mean? It means that the sound itself is having to cover a greater and greater area. Well, that thins it out. Much like the example of, let's say I get a little bit of peanut butter. And I'm very hungry, so I get a knife full of peanut butter and I put it on a nice cracker. So if I put it on the cracker and I eat it, the peanut butter is real thick and very, very good. Now the next day I come back and I take the same amount of peanut butter, but this time I went in the cabinet. And my brother ate all the crackers. Only thing that I have is a big old piece of bread. So I take the same amount of peanut butter and I put it on the bread. It was less satisfying because the peanut butter, when I spread it out, had to cover a bigger area. It wasn't as thick and as inviting as I thought it would be with the cracker. So the sound is doing the same thing. We got the same amount of sound, but as we get farther away, it doesn't have to cover more and more area, so it kind of thins out and kind of gets quiet. So the question is, what is this area? The area of a sphere, the surface area of a sphere, is 4 pi r squared. So if I ask you, how loud does something sound, what's the sound intensity, I would write I is equal to the power. The power of it, it would be low power, high power. So the power is actually the amount of watts, just like a light bulb is, that's propagated by the sound of that voice. How hard did you actually force that air out of your mouth? Was it powerful or was it kind of wimpy? All right? And that power, that sound wave as it propagates out, is spread out over an area that is 4 pi r squared. So this is our basic equation for finding the intensity of sound, if we look at that. And that tells us how loud things are at such and such a distance.